distance usually just means more time. Something farther away takes longer to reach. That's been reliable enough for most purposes. There's a straightforward assumption about distance, that anything reachable is just a matter of going far enough for long enough. If something is twice as far, it takes twice as long to get there. 1,000,000 times farther, 1,000,000 times longer. The relationship stays intact. This works for driving across a city, for light crossing between stars, for radio signals returning from spacecraft drifting past the outer planets. The numbers stretch. The time involved gets large, but the basic shape of it stays familiar. Farther means waiting longer. Light leaving Earth reaches the Moon in a bit over a second. The Sun in about 8 minutes. The nearest large galaxy, Andromeda, in around 2.5 million years. Long, certainly, but still just duration. Still motion through distance that stays put while the light moves. This gets used when calculating orbits, when timing, how long it takes signals to come back from distant probes. The numbers matter for real navigation. The logic has always held. But somewhere in the measurements of very distant galaxies, there's something that doesn't quite fit. It's small, easy to miss, unless you're looking at specific data about objects billions of light years away. The relationship between distance and time starts behaving differently. Not broken, exactly, just off. The space between things, at those scales, isn't fixed the way it is between Earth and the Moon. It's not even fixed the way it is between our galaxy and Andromeda. There's this expansion that shows up in the data. The measurements suggest that the distance between two far apart points grows. Slowly, while anything trying to cross that distance is still moving. So the gap a beam of light is trying to close. The measurements show it isn't the same size. By the time the light gets partway across, it's already larger. The light didn't slow down. Nothing pushed the destination farther away. The distance just increases continuously. And if the starting distance is large enough, the rate at which that gap grows can be faster than the speed of light. Not because something is moving through space faster than light, which can't happen, but the space between 2 points can stretch at any rate. Over a large enough span, that adds up. From the outside, it looks like a recession velocity, like one point is moving away from another, even though nothing is actually traveling anywhere. Which means, I guess there's a distance, somewhere out past the observable edge of things, where objects are receding faster than light can travel. And if that's true, then a signal sent now, from here, towards something beyond that line, doesn't arrive. The distance it's trying to cross grows faster than the signal moves. The gap widens while the light is in transit. It's still moving. It doesn't stop. It just never finishes, closing the distance. The remaining gap doesn't shrink to zero. It keeps moving through space that keeps stretching. The boundary where this happens, it's somewhere around 18 billion light-years out. Give or take, though, that number is less important than what it represents. That's roughly where recession equals light speed. Past that point, I guess distance becomes something motion can't cross anymore. Not because of fuel or engines. Just geometry. The structure of space itself, at that scale, makes certain destinations unreachable by anything, regardless of how long they travel or how fast they go. It's a strange thing to sit with, the idea that motion can continue indefinitely without ever completing the crossing. That something can keep moving, steadily, through space that's also steadily creating more distance to cross. There's no moment where the light stops. It just keeps going, the way light does. covering distance at the same rate it always has. And the total remaining distance stays out of reach. I guess you could try to picture it, like trying to walk toward something that's also walking away from you at the same speed, so the gap stays constant. That would be odd enough. But that's not quite it, because in that case, you're both moving here. The light is the only thing moving. The destination isn't going anywhere. The space just keeps being larger than it was. It shows up in the measurements as redshift mostly. Light from very distant galaxies arrives, stretched, shifted, toward the red end of the spectrum. That happens while the light is traveling. Apparently, the space it's moving through expands. The wave gets pulled longer. The farther away the source, the more stretched the light is by the time it arrives. And past a certain distance, past a certain amount of stretching, the numbers start suggesting something uncomfortable. That the source is receding faster than the light can travel. Which would mean the light we're seeing now from those places was emitted when they were closer than they are now. The light's been traveling toward us the whole time, crossing real distance. But the source has been receding the whole time too. So by now, it's farther away than when the light left. And if we sent something back, toward, where that galaxy is now, not where it was, I think the signal just wouldn't arrive. It would move outward, crossing space, doing what light does. But the distance would grow faster, so the gap would widen while the signal was in transit. Not by a lot, at any given moment, maybe, but persistently, steadily. And there wouldn't be a point where the signal gives up or stops making progress. It would just keep covering distance that keeps being created faster than it can be crossed. Which is hard to hold on to clearly. Maybe because motion usually closes distance. A car driving toward a city gets closer every second. Light, leaving a star, reaches the planets around it. Signals sent to spacecraft arrive after the right delay. The time involved might be long, but eventually there's contact. That's how it's always worked on smaller scales. Motion plus time equals arrival. Here, though, time doesn't bring arrival. Time just means more space to cross, because the crossing takes time and space expands while that's happening. So the destination recedes during the travel. The math handles it, apparently without anything breaking, but the intuition doesn't quite land. Motion happening without contact ever resulting from it. The boundary isn't sharp. It's not like there's a specific line where things suddenly switch from reachable to unreachable. Closer objects recede slowly, well below light speed. Farther ones recede faster. Somewhere between them, there's a distance where the recession speed equals light speed. Past that, recession is faster, closer, slower. The shift is gradual, but the consequences aren't. On one side, signals arrive eventually. On the other, they don't arrive at all. That distance sits out somewhere around, 16-18 billion light years. Something in that range. The number shifts depending on how the expansion gets measured. But the boundary exists regardless of the exact value. And it's not moving inward. Anything beyond it now stays beyond it. Nothing sent from here will cross that gap, regardless of how long it travels. There's something about the geometry that's hard to keep straight. Light moves at a fixed speed, well measured the same. Everywhere it's been tested, around 300,000 kilometers per second. So if the distance is stable, if it just sits there while the light travels, you can work out how long the crossing takes. Light leaving the sun reaches Earth in about 8 minutes, because the distance stays the same while the light is moving. But when the distance isn't stable, when it's expanding while the light is trying to cross it, I'm not sure the relationship holds the same way. The light still moves at the same speed, still covers the same amount of ground every second, but the total distance that needs crossing is different by the time the light gets partway through, larger than it was when the light started. So the light is making progress, covering real distance, but the gap keeps being wider than it was. Maybe the light crosses the space that existed when it started traveling, finishes that part of the journey. But while it was doing that, more space appeared behind it and ahead of it. So even though it's been moving forward steadily, the total span from start to finish grew. The light gained ground, the ground expanded faster, which would mean the light just stays in transit. There's always a remaining distance, always something left to cross. It keeps going the way light does, just never arrives, because the distance being crossed grows faster than it can be covered. So if you're waiting for a signal from something past that boundary, you'd just keep waiting, I think. The signal was sent. It's traveling, covering distance, but the gap keeps widening, always in transit, approaching because it's moving in the right direction. But the destination recedes faster than the approach closes ground. We can see light from galaxies that are past the boundary now. That light is arriving here, measurable, visible, which means it left those galaxies when they were closer, when the space between here and there was narrow enough that light could finish the crossing before expansion widened the gap too much. The light made it started early enough, finished before the distance became uncrossable, but sending light back now, toward where those galaxies are now. That wouldn't work. The distance is too large, the recession too fast. Light can come from there to here if it started long ago. Can't go from here to there now. We're receiving signals from places we can't send signals back to. I guess that means there are galaxies we can see, study, measure distances to, that we can't contact, can't send information toward. They exist in our observable past, so their old light reaches us. But they don't exist in our reachable future. The relationship only works one way. We see them, they wouldn't see us. Not because something blocks the signal, just the distance involved, the rate of expansion between here and there. And that boundary where sending something stops, meaning it arrives eventually. It's been there the whole time, probably for billions of years. But it doesn't come up much because most things we look at are closer than that, well within reach, receding slower than light. It's only the farthest observable objects, the dimmest galaxies at the very edge of what can be detected that sit near that line or past it. And the light we're seeing from them is old anyway, light that left when they were closer. We're not seeing where they are now. We're seeing where they were billions of years ago when the light started traveling. Where they are now is beyond reach, past the boundary, receding too fast. So the boundary marks off what's physically contactable maybe, not what's observable, because things past it can still be observed if their light started traveling early enough. But what's reachable? What could receive something from here? Past that distance, things are visible, but can't be touched. Observable, but outside the range of contact. And the strange part is that this isn't about technology. It's not that we haven't built something fast enough yet, or that we need better engines. The limit isn't in the tools. It's in the space itself, the structure of distances at that scale. You could send something at light speed, the fastest anything can go, and it still wouldn't arrive. The destination would recede faster than the signal could travel, so there's a maximum distance anything could ever reach. Not because of how it's sent, but because of where it's being sent to. Light traveling outward from here at 300,000 kilometers per second. Steady, continuous. Space expanding between here and very distant destinations, at rates that eventually exceed that speed. The light covering ground, the space creating more ground to cover. The two processes happening simultaneously. 1. Winning at small scales, where the light eventually crosses the gap. The other, winning at large scales, where the gap widens faster than the light moves. A competition between motion and expansion, with the outcome determined entirely by how far apart the starting point and destination are. Close enough, and motion wins. The light arrives eventually, after however many millions or billions of years the crossing takes. Far enough, and expansion wins. The light never arrives, no matter how long it travels. The transition between those two outcomes, sitting at a distance where the rates of motion and expansion exactly balance, where light speed equals recession speed, where travel becomes permanent and arrival becomes impossible. That distance, somewhere around 16 billion light years, 18 billion, the measurements carrying some uncertainty at those scales, at the boundary existing regardless of the exact number, existing as a feature of how the universe's geometry works when distances get large. Enough that expansion accumulates into recession velocities faster than light. There's something about the waiting, about what happens during the time it takes for light to travel. If you send a signal toward something and it arrives, there's a delay between sending and receiving. The farther away the destination, the longer the wait. A signal to the moon takes a bit over a second. Mars takes anywhere from a few minutes to 20 minutes or so, depending on where it is in its orbit. You send something, you wait, it gets there. And during that waiting, the destination stays roughly where it was. Mars moves in its orbit, but it doesn't suddenly end up twice as far away while the signal is traveling. The delay makes sense. It's proportional to the distance. The waiting corresponds to something fixed, but with things receding, I'm not sure the waiting works the same way. The signal starts traveling, moving outward at light speed. The destination is receding, which means the distance between here and there is growing while the signal is in transit. So the signal is covering distance, making progress, but the total distance that needs covering is larger by the time the signal gets partway there. The gap the signal is trying to close isn't the same size it was when the signal started. The delay isn't just about covering the initial distance anymore. It's about covering the initial distance plus all the additional distance that appears while the signal is traveling. The wait stretches, and the farther away something is, the faster it's receding, so the more extra distance gets created during the crossing. At some point, maybe, the recession gets fast enough that the distance grows at the same rate the signal is covering it. The signal moves forward, steadily, at light speed. The destination recedes, steadily, at light speed. And the gap between them just stays the same. Doesn't close. The signal is traveling, but it's not getting closer. The waiting doesn't finish. It just continues, ongoing, without resolution. And past that point, I guess the gap would actually widen while the signal is traveling. The destination recedes faster than the signal approaches. So even though the signal is moving toward it, the distance between them grows. The waiting doesn't just fail to finish. The signal gets farther from its destination. The longer it travels, even though it's moving toward it the whole time. Motion is supposed to close distance. That's how it's always worked, at smaller scales. You move toward something, you get closer. Eventually, you reach it. But here, motion happens without approach resulting from it. The signal is in transit. The destination is receding, faster than the signal travels. Separation, not approach. Distance, increasing, not decreasing. Things that are close enough that signals can travel between them are connected somehow, Information can move from one to the other. Events at one place can eventually affect events at another place. There's a link, even if it's delayed by how long light takes to cross the gap. You do something here, and the effects could reach there later. Something happens there, and the effects could reach here later. Causally connected, even across large distances, as long as the distances aren't too large. But past that boundary, the connection doesn't exist. Things happening here can't affect things there, because signals don't reach their things there. Things there can't affect things here, at least not from signals sent now. The two locations drift into separate regions, disconnected. Not by a barrier or anything physical, blocking the signal, just by distance, expanding faster than signals can cross it. And that disconnection stays, doesn't reverse. Things past the boundary now stay past that boundary. The expansion continues, the recession continues, the distance keeps growing. Things that are currently reachable will eventually cross the boundary too, given enough time. Objects that are still within reach now will recede past that critical distance. The boundary doesn't move closer, but things move past it, drifting from reachable to unreachable as they recede. So there are fewer destinations available now than there used to be, and there will be fewer later than there are now. Things drifting out of reach, slowly, one by one, as they recede past that distance where recession equals light speed. And once they cross it, they stay crossed. The distance only increases from there. The signals we could send now toward things that are close to the boundary. Those might be some of the last signals that ever reach those places. Send something now. It might arrive eventually, after billions of years of travel. Wait too long, and the destination might recede past the boundary before the signal gets sent. A window closing gradually for the farthest reachable objects. Not that it matters practically. We're not sending signals to distant galaxies. The travel times are too long, but the window is closing regardless. A slow reduction in the number of places that exist within reachable distance. Things drifting farther away, crossing the boundary, becoming permanently unreachable. You could send something at light speed, the fastest possible speed, and it still wouldn't reach destinations past the boundary. The limit isn't in what we send, or how we send it. It's in the space between here and there. The structure of distance at that scale. Space itself creates the limit. The boundary sits out there, maybe 16 or 18 billion light years away. Something in that range. Past that, recession exceeds light speed. And the universe keeps expanding. Things keep receding, so the boundary stays where it is, while more objects drift past it over time. The reachable region doesn't shrink in size, exactly, but it empties out, gradually, as things recede through it and cross into unreachability on the far side. Something moving steadily and never arriving. It's hard to keep that straight. Light traveling at light speed, crossing real distance, covering ground continuously, and the destination staying out of reach, not getting closer. The space between where the light is and where it's going just keeps being larger, and it's not just one signal. Anything sent toward destinations past that distance. Radio signals, particles, light itself, none of them arrive. They keep traveling through space that stretches faster than they can cross it. Distance itself, at that scale, becomes something motion doesn't resolve. The destinations are still there, is still existing, made of stars and gas, and whatever galaxies are made of. Still doing whatever galaxies do. They didn't disappear. They just ended up far enough away that space between here and there expands too fast. So they're out there, somewhere, but unreachable. Visible if their light started traveling toward us long ago. but separated by distance that grows faster than contact can happen. There are places that exist, that we can see evidence of sometimes, that nothing from here will ever reach. Not now, not later. The travel time doesn't just get very long. It becomes unending. The signal stays in transit, always approaching, never arriving. And from here, looking outward, toward those places. There's no way to close that gap. No way to send something that would complete the crossing. The signal would move through space the way signals do, steadily, continuously, but the destination would recede while the signal was in transit, so the separation would persist. Not because of anything blocking the path, just because of how distance behaves when it gets large enough. This has been true for a long time. The boundary sitting out there for billions of years. Not recent, but it doesn't come up often because most things we observe are closer, well within reach, receding slowly enough that signals would arrive. Only at the farthest observable distances, the boundary becomes relevant. And even then, the things we observe at those distances, old light from them, light that left when they were closer, we're looking at their past. Their present location is farther, receding faster, past the boundary or near it. We're surrounded by things we can reach, mostly the moon, planets, nearby stars, closer galaxies. Reachable, at least in principle, given enough time. Only the farthest edge of observable things, the most distant detectable objects. Those sit near that line where reachability ends. And they're so far away, their light so old, they barely register as present. Traces of where things used to be when the light started traveling, but also real places, existing now somewhere out there at distances we can't reach. Doing whatever they're doing, evolving however galaxies evolve. Disconnected from anything happening here. We can't affect them. They can't affect us. Distance to large, recession too fast, expansion too steady. They drift farther away, while we drift farther from them, and the gap widens. There's a maximum distance anything could ever travel in the universe, not because of fuel or speed or time, because of the space itself, the structure of how distances work at that scale. You could send something at the fastest possible speed, and it wouldn't reach destinations past a certain distance. The limit is built into the geometry. That distance sits somewhere out past the farthest things we can clearly observe. Farther than most galaxies we've catalogued. Somewhere in that region where measurements start getting uncertain and the light is stretched and dim. Past that boundary, destinations recede faster than light travels. Before that boundary, slower. The transition is gradual, but the consequences aren't. One side, signals arrive eventually. Other side, they don't. And things keep receding. The boundary stays where it is, roughly, but objects drift past it over time as they recede farther and farther. So the reachable region doesn't shrink in size, but it empties out. Things crossing from reachable to unreachable as they drift through that distance, where recession equals light speed. And once they cross, they stay crossed. The distance only increases. The recession continues. Places existing without connection. Light traveling without arriving. Distance growing between here and there. Steadily, continuously, with nothing to slow it or reverse it. Just separation, increasing over time. Carrying things from observable and reachable to observable and unreachable. Then, eventually, as they recede even farther, to neither observable nor reachable, just out there beyond the boundary, beyond the range where signals can cross, beyond the edge of what's contactable. There's no way to test it directly, I guess. No way to send something past that boundary and confirm it never arrives. The travel time would be too long. Billions of years. And even if you could wait that long, you'd need a way to know whether the signal reached its destination or not, which would require a return signal, which would have the same problem. So the unreachability isn't something you can demonstrate by sending something and watching it fail to arrive. It's something that emerges from measurements of expansion rates, recession velocities, distances, calculations about what would happen if you tried. And those measurements seem consistent. The expansion shows up in multiple ways: in the redshift of distant galaxies, in the relationship between distance and recession speed. The numbers fit together, but they're describing something happening at scales where direct confirmation isn't possible, where you're working from old light. Light that's been traveling for billions of years, showing you where things were when the light left, not where they are now. So when you look at a very distant galaxy, at the edge of what's observable, you're seeing it as it was a long time ago, maybe 10 billion years ago, 12 billion. The light has been traveling that whole time, and during that time, the galaxy has been receding, moving farther away, carried by expansion. So, where it is now, that's not what you're seeing. What you're seeing is where it was. And where it is now might be past the boundary, past that distance where recession equals light speed, beyond reach. But there's no way to check that directly, no way to observe where it is now. You only see where it was when the light left, and you can calculate, based on expansion rates, roughly where it should be now, how far it's receded since then. But it's a calculation, an inference. The light arriving now only shows you the past. And if you sent a signal back toward where you think that galaxy is now, you wouldn't get confirmation whether it arrived or not. Not for billions of years, anyway. And by then, even more time would have passed. More expansion, more recession. So the confirmation you're waiting for might never come. Not because the signal didn't arrive, but because the return signal can't make it back. Or maybe the original signal didn't arrive. There's no way to distinguish between those possibilities from here. So you're left with the measurements and what they suggest. That past a certain distance, signals don't arrive, that the boundary exists, that it sits somewhere out around 16 or 18 billion light years, that recession past that point exceeds light speed. But the boundary itself isn't something you can observe directly. You can observe galaxies at various distances, measure their recession speeds, see how recession increases with distance, and the pattern suggests a threshold, a distance where recession would equal light speed, past which arrival becomes impossible. But proving that, I don't know. You'd need to send something and have it not arrive, and then somehow confirm that it didn't arrive, which you can't do if it didn't arrive. So the unreachability is something inferred from the geometry, from how expansion works, from the relationship between distance and recession, not something you can test by attempting it. And the destinations themselves, the places past that boundary, they're still there, presumably, still existing, still made of matter, still doing whatever distant galaxies do, just beyond the range where contact is possible, beyond the range where anything sent from here could reach them, and there's no signal they could send back that would tell you whether that's true or not. Because signals from there don't reach here either, at least not signals sent from their present location. So you're observing a past that reached you, but cut off from a present that can't. Seeing evidence of places that exist, or existed, without being able to interact with them in any current sense. The light from them keeps arriving. Old light, getting older and dimmer as the sources recede farther away. But the places themselves, where they are now, those drift farther into disconnection. Observable in the past, unreachable in the present. And I guess that makes the boundary feel less like a line you could point to, and more like a transition that's already happened, maybe, or is happening continuously. Things crossing from reachable to unreachable as they recede. One by one, gradually, without any clear moment where the crossing occurs. Just a slow drift from one state to another, from causally connected to causally separated, based on how far away they are and how fast space expands between here and there. Distance usually meant waiting, and waiting usually meant arrival eventually. Something twice as far took twice as long to reach. That relationship held for most things, most distances. Light crossing between the Earth and Moon, between the Sun and planets, between stars. The spans involved might be large, the durations long, but the connection between distance and time stayed consistent. Farther meant longer, but it still meant reachable. And that's still true for most of what's observable, most of what gets measured and studied. Nearby galaxies, distant stars, objects millions of light years away. They're all receding, carried by expansion, but slowly enough that signals would reach them eventually. The waiting would be long, extraordinarily long in human terms, but finite. The distance could be crossed, given enough time. Motion would produce approach, gradually, and approach would produce contact. But somewhere past a certain scale, past distances where the numbers stretch into tens of billions of light years, the relationship changes in a way that's hard to hold on to clearly. The waiting stops corresponding to anything finishing. Signals keep traveling, moving through space at light speed, the way they always do, covering distance steadily. The destinations keep receding, carried by expansion, growing farther away while the signals are in transit. And the gap between them, the remaining distance that needs crossing, it doesn't shrink. It grows or stays constant, depending on how far away the destination is. The motion continues, the travel continues, but the approach doesn't happen. And there's a distance where that transition occurs, where recession velocity equals the speed of light, where signals sent from here wouldn't arrive no matter how long they traveled. That distance sits somewhere out past the farthest clearly observable galaxies, out in that region where the light is very old and very dim, and the measurements start carrying more uncertainty. The exact number shifts, depending on how expansion gets calculated. But it's somewhere in the range of 16 billion light-years, 18 billion, something around there. Past that boundary, destinations recede faster than light can travel toward them. Before it, slower. The division is gradual, but the consequences aren't. Things keep drifting past that distance as they recede farther away. One by one, slowly, carried by expansion that continues steadily. The boundary stays roughly where it is. Objects move through it, and once they cross it, they stay crossed. The recession doesn't reverse. The distance doesn't decrease. The separation only continues growing. So there are fewer destinations within reach now than there were in the past, and there will be fewer in the future than there are now. The reachable universe emptying out gradually as things drift from one side of that boundary to the other. And the light from very distant galaxies keeps arriving here. Light that's been traveling for billions of years, showing where those galaxies were when the light left, not where they are now. Where they are now is farther away, receding faster, possibly past that boundary already. The light made it, the galaxies didn't stay reachable. So there's this asymmetry where old light keeps coming in from places that aren't reachable anymore. Places that exist somewhere out there, but beyond the range where any signal sent now could reach them. The signals would keep traveling if they were sent, moving outward through expanding space, covering distance the way light does, steadily, continuously. The destinations would keep receding, growing farther away, carried by expansion that doesn't stop. And the space between them would keep stretching, creating more distance faster than the signals could cross it. So the signals would stay in transit indefinitely, always approaching but never arriving, moving through space that expands ahead of them as they travel. Just light, moving through expanding space and distance growing, while the light moves, and destinations receding, while signals travel toward them. The motion steady, the expansion steady, the gap widening. No moment where that changes, just ongoing travel through space that continues stretching. Distances that continue growing, recession that continues carrying things farther away. Light in transit, destinations receding, space expanding between them.